Some key ideas for circular motion. If you're moving in a circle, what direction is your acceleration? Toward the center or inwards. What direction is the net force? FC. No. What direction is your acceleration? Toward the center. So what direction is your net force? Because that's the winner minus loser equal MA. That's the MA part, toward the center. What direction is your speed? The fancy phrase is tangent to the radius, perpendicular to the radius. I think I got a picture here. These are a lot of my test template questions. Let me see, Mr. Dewick. Maybe I don't. Here. Heck, you might even see the same diagram tomorrow. I don't know. Okay? What is direction 2 telling us? What is arrow 2 showing us the direction of? Okay, see the pictures? We have 1, 2, 3, 4. Yes? Arrow 2 does tell us something. What's that the direction of? So arrow 2, that is the velocity direction, tangent to the radius. What's arrow 1 telling us? Are we sitting on a surface here? I don't think so. What's arrow 1 telling us? I'll give you a hint. It's a trick question. Okay, I'm going to say, Deegan, that's a bad guess, because which way is FC always pointing? Toward the... So is direction 1 pointing towards the... No. So don't say that. Nothing. That's a distractor. That's what a lot of people think. They think they're getting pushed outwards, but we've said, no, no, no. That's your inertia actually wanting to keep going in a straight line. But because you're not used to having to pulling yourself to stay in one place, you think you're getting pushed outwards. Okay? What's arrow 4 telling us? What direction is that if we're moving in a circle? What's that telling us? Yes? Yes? And which is F net in our free body diagram. Is that okay? What's arrow 3 telling us? Nothing. It's just there to distract you. 45-degree angle, not pointing along the center? No. Is that all right? Yeah. So that's absolutely going to be, some version of that is going to be a multiple choice-y, kind of a question-y. Okay, maybe a picture like this. I got a few of these that I picked up over the years. So there's that one. And, oh, hey, here. Which one of those tells us the direction of the acceleration? What letter? What letter tells us the direction of the velocity? Because I asked you to. What letter tells us the direction of the velocity? Why? Because I asked, what letter tells us the direction of the net force? W. Why? Because if you're accelerating that way, towards the center, that must be the net force. What letter tells us the direction of FC? W. What are Z and X? Distractors. What do a lot of people think the direction of the net force is? A lot of people will think it's Z. That's what, when they talk about centrifugal force with an F, that's what they talk about. It's not a force. It's your own body's inertia. You saw the videos on the Coriolis effect, and we saw how, yeah, it's not a force, but it sure does look like one, because it makes it looks like things are moving or turning. Is that all right? Okay. Then we talked about vertical circles. This will work. Heck, you might even see the same diagram tomorrow. I don't know. Oh, sorry. One more thing. How do we calculate centripetal acceleration? 2 equations. Which ones? You don't need to memorize them. They're on your sheet, but you need to know where they are. Which v, by the way, that v is your circular, your tangent to the radius speed. It's the arrow 2 speed. And you can calculate that arrow 2 speed. That's a terrible c. That's supposed to be a c. You can calculate it by going 2 pi r over the period. There's one more version of AC. What's the other one? Which of these is FC? Neither of them. How can acceleration be a force? How can I turn an acceleration into a force? F equals what? So if I want this to be in a force equation, better put an M there, better put an M there. Okay, don't forget the M. Especially this one, kids, forget the M because it looks so complicated. It must be a force. It's an acceleration. It's an acceleration. Then we talked about, so what are you going to see for vertical circles? Well, one is something like this. Okay? Except I can make that bigger. There you go. So what can I give you here? We can either be at the top or at the bottom. We'll do one of each. And I can either give you the speed and say, find the normal force, or I can give you the normal force and I can say, find the speed. Okay? So let's do the second one first. Supposing we say something like this. At the top, a person of mass 46 kilograms feels, I don't know, 3 times their weight. How fast are they traveling? First of all, what is this question asking us to find? Okay? What path are we tracing out? Free body diagram. What are the forces acting on this person at the top? Get the obvious one. What else? Which way? Whichever way the head is pointing, which in this case is downwards. What about for the Ferrous wheel? For a Ferrous wheel, your head is pointing up and the normal force will be pointing up. And we'll look at one like that in just a second too. But for now, I would have this. Who's winning? I gotta be fussy. Yes. They both are. Who's losing? No one. Okay? That's important. So what's my equation gonna be, Deegan? And because they asked for speed, probably v squared over r. Yeah? Okay. Do I know m? Yep. Do I know g? Yep. I don't know the normal force. Or do I? What phrase haven't I used yet that this question gave me? So what's their normal force? More specific. I gotta be fussy. 3 times mg. You kept saying their weight, but what's their weight is mg. They're gonna feel 3 times their weight. In fact, it's gonna be mg plus 3 mg's equals mv squared over r. And I could start plugging in numbers now, but you know I love to see if I can simplify. What's 1 mg plus 3 mg's? What does the left actually work out to? You can gather like terms. 4 mg's. Right? And that makes sense. All of you right now are experiencing 1g right now. So if you're feeling 3 times heavier, that's actually 4 g's on you. Okay? So we have this. 4 mg equals mv squared. In this case, will a little kid and a grown-up all feel 3 times heavier at the top? Yep. And okay, either I could ask you to find r. I forgot to give you r. So at the top of 18 meter radius loop, there's my quick workaround. Or I could have given you the speed and said find r. You can get either of them by itself, because for this specific one, we have 4g equals v squared over r. How would you get the r by itself? And then move the 4g to the bottom? How would you get the v by itself? It's our old friend, the square root of 4 this time, but okay. I don't remember if I put one like that on the test on the multiple choice. I know on one of my multiple choice versions, I have them find g. So for what it's worth, how would you get g by itself if we were on a different planet? Don't overcomplicate. How would you get the g by itself? Divide by 4. In other words, I think you can get the g by itself. I know in previous versions of tests, I've given them a multiple choice question where just for giggles, I said, we're going to go to a different planet. Let's find g on that mystery planet. Don't think I put that one on yours this time. But I can't remember because it was on the weekend and I'm tired. Sorry. Is that okay there? Now, that would be if they gave me the normal force, or I could ask you to find the normal force. So I could say, same picture. At the bottom of a 14-meter radius loop, a person of mass 62 kilograms has a speed of 21 meters per second. What would, well, you know what? I would probably say this. What is their normal force? But I question mark. But I could also say if they were sitting on a scale, what would the scale read? Because what does a scale measure? Normal force. I think there's a Ferrous wheel question where I have the person sitting on a scale and I expect you to make the one more. Oh, he's not talking about a scale, he's talking about a normal force. Okay, now we're at the bottom. Sorry, we don't need the car there. We can imagine it there. This is a job for us. What are the forces acting on it? Get the obvious one. What else? Which way? Bigger, smaller, or the same size as mg? Why? What path are we tracing? A circle, winners towards the center. I'll exaggerate it so it catches my eye. We talked about how no one actually builds circular loops. Okay, this may be fatal because I just made up numbers. This person may be pulling more G's than we would ever like, or this may be impossible. I haven't run the numbers. 21 meters per second here might not be enough to make it over the top. So if you take this further when you're at home, or for those of you watching on YouTube, I just made this up. I haven't proofread the numbers, so this ride might not work. Full disclosure. Okay. But anyways, what would my equation be then? I guess normal force minus mg equals mv squared over r. What do they want me to find? So I think I would plus that. And then it's just going to be 62 times 21, don't forget the squared, divided by 14 plus 62 times 9.8. I have to crunch this to see how off I am. 62 times 21 squared divided by 14 plus 62 times 9.8. What did I type in wrong, Mr. Duick? Oh, answer button? Really, Mr. Duick? 62 times 21 squared divided by 14 plus 62 times 9.8, and I get 2,560. If I divide that by m, that gives me their acceleration. If I divide that by 9.8, that tells me how many G's. They would survive this, but I also know this coaster wouldn't make it through the top. Sorry, because it needs at least 6 G's on the bottom to make it through the top. So, sorry, don't ride this ride. Anyways, I got 2,561. 2,560.6 newtons. Is that okay for the roller coaster? So when I said roller coaster loop, this is the part that I mean, the snapshot. I'm not going to give you the question that we did where we started on top of the hill. That was really cool. I think that was lesson, yeah, I called it cool applications. It was lesson 5. And we found that when we crunched the numbers, a whole bunch of stuff canceled. Even G canceled, and we found, oh, the hill has to be 2.5 times your radius. That was a lovely answer, but oh, and so much work to get there. Cool, but not fair for a test. Okay? What's the other big vertical circle? Okay? By the way, if you, again, do a Google search or a Wikipedia search for the word Ferris wheel, find the history of the first one, built by George Ferrous. The very first one built was over 80 meters high. That's high. 80 meters, you're looking at about, 80 divided by 3, about 25 stories high. It was built for I think the 1890 Chicago World's Fair. At that time, the tallest buildings in Chicago were only a few stories high, and then you had this ride 25 stories high. It was like the talk of America when it went up, and people stood, pardon me? 1890-ish. Okay? It's for the Chicago World's Fair. At one point, it was so big, at one point, I think something like half of the steel production in the eastern U.S. was being devoted just to build that Ferris wheel. He had to get financing from several banks because everybody thought he'd lose his shirt. He ended up making a mint because people lined up for hours. It never stopped running. The number of passengers it held, I think 1,800 passengers. Each car, I think there was, I'm going to get my numbers right, 24 cars, and each car held something like 80 people. Like, they were huge cars. And it went slow because the big point of this was no one had ever seen a view that high before. So the whole ride itself, I think it lasted 12 minutes or something like that, turning very majestically. And again, people stood in line for hours for it. Even now, that would be an impressive Ferris wheel. We've built a few bigger since then, but not many. Hashtag nerd trivia. Meanwhile, I'm riffing on Ferris wheels. Show me a picture of a Ferris. Was that a Ferris? No, that's a spaceship. Gravity. Gravity. Roller coaster. You may see this very same picture. I don't know. So what can I say? I could say something like a Ferris wheel of radius, Mr. Dewick. Better yet, let's find R. At the top of a Ferris wheel, a person of mass 62 kilograms sits on a scale. The scale displays a mass of 51 kilograms. If the Ferris wheel rotates once every, takes Ferris wheels a little while to go around. Let's make this one a little more exciting. Let's say once every 12 seconds. Find the radius of the Ferris wheel. Is that all right? Can I get this all on one page? Can you read the writing? Can you read the font from back there? Is that okay? Okay. We're at the top. Pretty sure we're going to do a free body diagram. All right. What are the forces acting at the top? Get the obvious one. What else? Which way? Pointing up this time, yes? Yoink. Okay. Who's winning? Who's the loser? Equals M-O. Since they mentioned the period, 4 pi squared r over t squared. Is that okay, fellas? You with me? Yeah. What's M? Yep. What's G? By the way, I'm trying to get the R by itself. This is complicated enough. I'm going to turn this into a single number on my calculator first. Then I'm going to get the R by itself because this is yucky. Doesn't look like the M cancels. There's not an M in everything. What's G? What's the normal force? Well, first of all, what does a scale measure? What did the scale read here? Is that a force? What are the units next to that 51? How do I convert a force back to newtons? Okay, so it's going to be minus 51 times 9.8. That equals m4 pi squared r over t squared. As far as I'm concerned, on this line here, I can either give you R and T and say find the normal force, or I can give you the normal force and R and say find T, or I can give you the normal force and T and say find R. No matter what, if I'm finding R or T, I would probably crunch the left side. Finding the normal force, I can get the Fn by itself, swappy dance or whatever. That's not a big problem. But to get one of these by itself, I'd probably turn this into a single number first. And I'm going to do that right now. 62 times 9.8 minus 51 times 9.8. 107.8. That's better. So I get 107.8 equals m4 pi squared r over t squared. And now I have one fraction equals one fraction because this is over 1. So stuff can move diagonally. That's going to go there. That's going to go there. Here the m doesn't cancel because that m was different. And typically if you're including the normal force, usually the m won't cancel. Unless you've been able to write the normal force in terms of mg like we did in this one here. Well, then the m canceled. But usually little kids don't feel rides the same way adults do. You feel much bigger forces if you're the grown-up. R is t squared times 107.8 divided by m 62 for pi squared. You know what? T was 12. Again, I just made these numbers up. I'm hoping I don't get a radius of like 5,000 meters and make an impossible Ferris wheel, but we'll find out. 12 squared times, answer button, divided by bracket 62 times 4 times pi squared. That's not bad, because that's the radius from about me to Prab is around 6.3. The diameter then will be twice that. Sure, that's a small Ferris wheel, but sure, that works. A little portable one that you might bring from town to town as a carnival, or a kiddie one, maybe. 6.34. Would you be okay if we were at the bottom? How would your free body diagram be different at the bottom? What are the forces? Get the obvious one. What else? Who'd be winning? So it would be Fn minus mg equals m whatever AC you happen to need to be using. Okay? Is that all right? Okay. Those are, I think, the two main ones for vertical circles. There is also a mass on the end of a string, and I may come back to that if I have time, but I want to get to... And the big one that you're going to see is the Gravitron. The Gravitron is both cool and... Ooh, I have one right here. That's convenient. And very tricky. Okay? So what can I ask you? Out of R, V, T, and mu, I can give you 3, find the 4th. Okay? Really, it's I can give you 2, find the 3rd, because you're either going to be given or use V, or you're going to use the one with the T in it, but you're not going to use both. So let me give you an example. Again, totally making this up here. Gravitron has 0.076. That's way too big, Mr. Dewick. Let's make it a safer ride, because otherwise people would have to be wearing Velcro. And radius of, I've been on the Gravitron, I think the radius is about from me to Owen, because I think the ride itself was about twice as big. So I'm going to say, I don't know, 11 meters. Find the... I don't know. Just last week, we got the updated field trip COVID protocol from the district. I'm not trying to get through that. Like, it's a catalog. So if it's still like that, as much as I love you guys, the amount of effort and hoops I'd have to jump through because we're going to a crowded area with strangers, right now, no. But I'm hopeful it will change dramatically, especially once better weather rolls around. You might recall we noticed last year, once people were outdoors more, and just the UV from the sun rays actually deals with outdoor COVID viruses much better too. Okay, find the period of rotation for this ride to safely operate. Probably we're finding the minimum period of rotation. It could spin in less time. So I might put the word minimum in front of the word period. I don't know. What is this wanting us to find? What symbol or what concept or what letter is that? Okay. This is a job for a free body diagram. All right. Here's the person. What are the forces acting on them? Which way? Okay. What else? Which way? And that's the weird aha moment. Because I know there has to be a force pointing that way. Which force is that? Yeah, and this would be the same, I don't think I put one on the test, but the space station artificial gravity was just that. But it was still the normal force creating the fake gravity. On the Gravitron on Earth, the normal force is also creating the fake gravity, but we need something to cancel out mg for the ride to run safely. So what we have here is this. Normal force is what's pushing us in a circle. I guess because they mentioned period, I'm going to use m4 pi squared r over t squared, but I don't know the normal force. However, there's another equation, a vertical equation. Are we sliding down? Are we sliding up? That must mean that mg equals friction. mg equals mu times, that's a terrible n, the normal force. Strangely, instead of the normal force being, oh, but look, I don't know the force the same size as, I don't, but I can tell you that the normal force has to be the same size as mg over mu. And I can plug that into there. And I'll get mg over mu equals m4 pi squared r over t squared. Can little kids and grown-ups go on this ride? Well, that's cool. Could you get the mu by itself? Yes, I might ask for that. Could you get the r by itself? Might ask for that. Could you get the t by itself? Yeah. For giggles, could you get the g by itself? I didn't ask that, but it would certainly, to me, not be a stretch. Oh, let's put this on another planet. What would G be on the other planet for this to run safely? Is that all right? What are we trying to find? Where is the period right now? Blech. T squared goes there. G goes there. Mu goes there. And then how do I get rid of a squared? So it's going to be 4 pi squared r mu over g. Whatever the heck that is, let's find out, because I kind of like to know the answer. It's going to be 4 pi squared r 11 mu 0.35 all over 9.8. I hope I haven't made an impossible ride. When I make these up, I'm trying to do some quick math in my head and make some rough guesses, but this is pretty complicated math for me to do in my head. Yika. Well, okay. Rotates every 3.94 seconds, which little fast maybe from what I recall of the Gravitron. I think it rotates about every 6 or 7, but I'm ballpark. 3.94. So those are most of the written questions, and that's most of the multiple choice stuff. The only other thing on the multiple choice, I think I gave you a question where I either give you FC and ask you to find V or R or T or M. In other words, you can go straight with, in the same way that if I say F net, you can go straight to a what force, F net, a what for, MA. If I say FC, you can go straight to F equals M AC, and depending on whether they ask for or give you the V or the T, get whatever you want to by itself. No free body diagram required. I think I put one of those. In fact, probably going to be number 1. Or number 1 might be a directional question. That's just a guess off the top of my head, but that's probably how I would set it up. Is that all right? Okay. Any other specific questions? Oh, car going around a corner. Horizontal circle. The easier horizontal, yes, sorry. Car going around flat corner. And the reason I'm adding that is normally I also do a banked corner, but I had to cut corners. Ha, 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 that's funny, Mr. Duick. Car going around a corner. Show me a car going around a corner. Hey! That'll work. Maybe I got a better picture than that, because that one's really big and ugly. You know what? I don't think I do. I would probably not even give you a picture. I would probably say something like this. A car is going around a flat horizontal, a flat circular corner at, I don't know, how fast in meters per second? Deegan, give me a number. Holy smokes. Okay. What must the minimum radius of this corner be for the car to make it through safely? For the record, 75 meters per second, that's, well, could you multiply that by 3.6? How many kilometers per hour? It's going to be a big radius, okay? That's fine. But we're talking, this might even be a radius bigger than a kilometer. I don't know. But this is going to be a pretty big radius. Don't drive with Deegan. Don't. The key for this, Deegan, is the free body diagram. We said a top view doesn't work very well. A much better view is this one here, where you have the car coming out of the page towards you, going around a corner. Because what are the forces acting on this car? Get the obvious one. What else? What else? Which way? Somewhere on the written, I will ask you to draw a free body diagram for something as well. Oh, heck, probably roller coaster, Ferrous wheel, or Gravitron. What's my equation? MAC. Which version of AC am I going to use? Looks like they gave me the speed, so Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. Can little cars and big trucks go on the same road? Looks like here they asked me to find R. Okay. V was the square root of mu ger for this particular one. I don't memorize that. I can derive it. Here, where's the R right now? On the, okay. How do I move it to the top? I think I'll go, that goes there, and that goes there. Pardon me? I did not. Good. With very good point. See, if I make this slippery, then we're really going to get a big radius here with Deegan's little race car. So, let's make it a little bit slippery, just for giggles. How about 0.36? What must the minimum radius be? Okay. Wow. R is going to be V 75 squared divided by 0.36 times 9.8. 75, Deacon. Jeez. Yeah, it's over a kilometer. Okay. If you don't build it at least that large, people will not be able to navigate the corner under these conditions. Well, probably your better bet, yeah. I mean, you can either build a road with a curve more than a kilometer wide, or you can put up a speed limit sign. I'd probably choose the second one, a little cheaper, safer. 75. Wow. Okay, I think that's pretty much for the written. Are there any specific questions from the homework you would like me to go over? If not, I'll stop the video, but we can stay another 5 minutes or so. No, there used to, on the provincial, used to be one graph they had to interpret every time. And so I used to, in the work energy lesson in Physics 12, I used to end it with, here are tricks to interpret graphs. I didn't cross out the graph questions from your review because I'm hopeful I'll cover it next year with my students. But you're asking about the one, here's a hint. A circular acceleration is v what over r? It's going to be a parabola if you're graphing a versus v, because it's a squared. So pick the one that looks like a parabola. The same with kinetic energy is a half mv squared. If you're graphing ke versus v, it's going to be a parabola. Little tricks of the trade that I've learned over the years. But I'm not going to specifically ask you to interpret a graph, no. I'd like to, but something's got to give. So that Tarzan swing number 6, I think it's number 6, that's a really, really tough question. Let me show you my solution key for that one, Mr. Dewick. Okay, because this one you also had to bring in conservation of energy, and I'm not going to give you a big combination like that. This Tarzan one is really similar to the roller coaster loop cool applications, lesson 5. I thought it was number 6. Maybe it was number 10. Okay. The left part, this part here to me is fair game in that I would expect you, if we're swinging something in a circle, you could say, what are the forces acting on it? This free body diagram to me is fair game. What are the forces acting on it? Gravity down, and we're moving in a circle, so I know tension is winning. And so that would be fair game. That would be fair game. But then I would give you enough information, so I would either give you V and R and say find tension, or I would give you tension and V and say find R, or I'd give you tension and R and say find V. That would be fair game, although I don't think I put it on your test tomorrow, but that would be fair game. The nice thing here is when you get to this line, you're, wait a minute, they didn't give me V. Well, is there a change in height? Is there a change in speed? Is there a conservation of energy? On this horizontal rope swing where we're starting with it level and then jumping, all of your potential energy is turning into kinetic. All of your potential is turning into kinetic. And I said, if I can find V, that's that V there. I found that V squared was 2 Ger. Why didn't I find V? Because there's a V squared there. So I replaced that V squared with 2 Ger. Hey, the R's canceled, and I ended up with mg plus 2mg. I ended up with 3mg. Now, what does that really mean? How many of you ever swung on a rope swing? Okay. How many of you ever swung on a rope swing where you started horizontally and then jumped off and swung? None of you. But if you did, at the bottom, how many G's are you having to pull? 3. In other words, if you'll see a lot of the videos on YouTube, people on a rope swing, and near the bottom, their hands give out and smack into the ground. Well, that's why. Because here, you're having to pull, right? That's like basically, you have to be able to do a chin-up with 2 of you on your back. I don't think any of you are doing that. So that's why that was kind of a neat question, but I'm not asking you one with all of this stuff as part of it. No. Is that okay? Any others? Oh, I put number 10 on here twice for some reason. Okay. That's digital, who cares? Which was the graph question? What number was that? Yeah. So it's A equals V squared over, you know what? It's V squared, it's parabola. You kind of pick up some tricks of the trade after you've done a bunch of these where, yeah, I can tell what it would look like. I don't know what numbers would be on there, but I can tell you the shape. But no, I'm not going to ask you a graphy interpretation question. Question 34. Too far. Sure. What do they want you to find? Keep going. It's called a distraction. You can handle it. That's like the net force. You can go straight to F equals MAC. You notice I didn't do a free body diagram. I went straight to M. Oh, they gave me the 4 pi squared R over T squared. Plug and chug. There's going to be one like that, although probably, it'll be a multiple choice, probably I'll give you FC and I'll ask you to get the M or the R or the T or the V or the R by itself, depending on what I give you. I think that's one of the multiple choice ones. And again, if I say the net force or the centripetal force, you don't need to do a free body diagram. You can jump straight to the punchline. FC equals MAC. Get whatever you need to by itself. Right? 35 to me would be fair game. Only because, well, yes and no. Minimum speed, you want the normal force to be 0. So normally it would be a normal force pointing down as well. Yes? Lesson 5. Question 5, part B. Okay, I might have to pass on that, but we'll see. Lesson 5, question 5, part B. I know I gave you some tricky questions in the homework here because I wanted the homework to be tougher than the test. Part B. So part B, I'm not going to ask you on your test, but here is your hint. Part B is identical to the procedure we did to find the minimum height here, but with different numbers. So it's just like example 1. I'll let you try and figure it out from there. Okay? There's my alarm saying I got to go soon. Okay? Before you go, first of all, let me pause the video.